So thanks everybody for coming. Today we have Richard Tuminello, who is going to present some results, things from maybe getting a preview of some later slides there. We'll have one from his work with the ICON mission. So with that, take it away.
All right, thank you very much, Kevin. Let's go ahead and get started. First of all, hi, I'm Richard Tuminello. I'm a first-year PhD student. My advisor is Dr. Scott England, and I would like to shout out Dr. England, not only for helping me with all the research you'll see, but for helping me get ready for this presentation as well. So without further ado, let's just go ahead and get started. We're going to be looking at ICON, which is the Ionospheric Connection Explorer, one of the newer NASA Explorer missions. So I'll let you go ahead and take a look at this outline on the left if you want. This photograph on the right, well, it's not a photograph, it's an artist's rendition of ICON. So this is launched in late 2019. So most of the data we're going to be looking at is from 2020. And so, you know, in the time scale of these studies, this is a relatively new thing, and it's something to be excited about if you have any interest in studying the ionosphere. So what we're going to do is we're going to kind of break it down into three parts, starting talking about the upper atmosphere and the ionosphere as a whole, and you know, maybe why we're interested and what we're interested in studying. And next, we'll take a look at how we're going to study those things with ICON. How will ICON allow us to get the data that we want? And then finally, we're going to look at the research that I've been working on. So, which is not necessarily related to the main science goals of ICON, but we'll get there when we get there. All right, so into part one. So the upper atmosphere extends out into what we would consider to be space, right? The Kármán line at 100 kilometers defines the beginning of space, but we have this extended atmosphere, and in particular, the region we're looking at is the thermosphere. That's going to extend into this figure here, you know, 500, 600, 700 kilometers. And part of this region constitutes the low Earth orbit. Right? Low Earth orbit will extend beyond this, but part of low Earth orbit is in here. So if you have a satellite flying through this region, you might be interested in the physics that is taking place. For example, if you're concerned about satellite drag or surface charging or any sort of radiation effects. And in particular with the ionosphere, radio. If you want to send radio waves through the ionosphere, you'll have to keep in mind what frequencies will be available and which can get blocked. So from an engineering perspective, there's certainly some use in the study of the ionosphere. And I keep mentioning the ionosphere and the thermosphere. These are overlapping regions of space. The thermosphere referring to the neutral atmosphere, and the ionosphere being the plasma environment. The plasma itself is generated by solar UV. This is photoionization of these particles. But the sun is not the only thing that's going to change the structure and evolution of our ionosphere. So that's part of the thing we're going to study. Okay, so as a bit of a primer to what ICON wants to look at, we're going to examine one of the principal features of the low latitude ionosphere, and that would be the ionospheric equatorial anomaly. I think I'm switching some words around there, but I will refer to it as the equatorial anomaly, which you can see over here off to the right. Now, the generation of this, we can talk through starting from the left. There's a pattern of neutral winds that are at thermospheric altitudes going eastward. Right, these are neutral winds, and in the same space we have plasma just hanging around. So the ions have a high cross section for collision with neutrals, and as a result, they can get blown to the east by this neutral wind. But the electrons do not have a large cross section of neutrals, and as a result, for the most part, they don't see them. They don't start having this eastward velocity like the ions do. So having established a difference in velocity between ions and electrons, this is now a current. Our current sets up an electric field. So being mindful of the fact that we have an electric field from this differential velocity, we have a magnetic field from the Earth that's pointing northward. And if you've ever studied plasma science, you know that this can set up a drift, a plasma drift, in particular the E cross B drift in the direction of E cross B. So we have our electric field crossed with a magnetic pointing north, and that's going to give us an outward ion drift away from the Earth's surface, represented by these green arrows here. Now, to take a look at this plot in the middle, this is a measure of that ion drift for some different seasons. So you can see different times of day, we can expect different magnitudes of this upward drift. So the plasma drifts upwards, and it flows out from here like a fountain. We call this the fountain effect. And then after, fountaining upwards, it slides down these magnetic field lines and collects off of the magnetic equator. So the result of this process is that instead of having one peak of ionospheric density, there are two separate peaks on either side of the magnetic equator, right? And this is the equatorial anomaly. So that's pretty cool, but this is in fact the textbook version of that story, and the real life version is much more complicated. These vertical drift profiles vary significantly from day to day, as shown by these plots here. And as a result of that variation in vertical drift, we get different structuring of the ionosphere, right? So these three images are total electron content in a way. It's the plasma density for 3 consecutive days, right? And you can see on this first day, we have something that looks like, what we would expect, our normal equatorial anomaly. But going from, one day to the other, we can see the peak isn't as strong here. And on the third day, we only have a single peak, right? So this change in vertical drift is affecting the structure of the ionosphere. All right, so we can see the effects of these changes in vertical drift, but we have not discussed what the cause of that change may be. So there's 2 factors to consider if we want to study the variability of the system. The first of which would be variations in solar energy deposition coming from the sun into our upper atmosphere. And then the second will be waves that propagate up from the lower atmosphere into our thermosphere. So we're going to go ahead and take a look at each of these in a little bit more detail. And that's going to lead us into ICON's mission to study how these are affecting the structure of the atmosphere. All right, so if we're going to talk about solar UV, then importantly, we should talk about absorption. So first, I would direct you to this plot on the top left, and there's kind of a lot going on here. You have the atmospheric layers and all sorts of information, but I would point your attention to this curve here. And this curve is just showing where we would expect the radiation to be absorbed as a function of wavelength, right? Wavelength in angstroms, everything we're looking at here is the UV. Visual light would be 4,000 angstroms, right? So we're in the mid and far and extreme UV here. And as you can see, at our altitudes, the emissions that are getting absorbed are these high energy photons in the FUV and EUV. And that's really shown as well in this plot down here. This is showing how much energy is being deposited at each wavelength, now in nanometers. And you can see that if we look at our altitudes of concern above 100 kilometers, the wavelengths that we really need to be concerned about are this EUV and this FUV, right? And we're going to get into more details in this on the next slide, but this plot on the right shows the consequences of variation in UV, right? These high energy photons are variable in flux, so that when we have solar minimum, the least amount of UV flux, the temperature is significantly lower than its solar maximum when we have more solar UV flux. All right, so here on the left, we have a plot of radiance given against wavelength. And this curve here is the black body curve that you would expect, given by the temperature of the surface of the sun. And this is a very good reference for what kind of spectrum we expect to see from the sun, especially from the photosphere, the sun's surface. And this component of the solar radiance is very constant over time, right? It does not change too much. We can pretty much count on it being the same every day. But these components that lie outside of this range, which constitute, as you can see, peaking at visible and then a lot into the infrared and just a little bit into the ultraviolet, if we get outside of this range, we get into the area that's dominated by solar activity that is above the solar surface, right? Such as solar flares, which you can see in this nice little movie. So solar flares and prominences and all of these things that are sticking out of the surface of the sun will be generating this higher energy radiation, as well as the lower energy radio, which we may discuss later, that there's a connection between radio and UV that is helpful to us. Right, so let me talk about this 1 second. The black body portion is very constant, but these other portions are highly variable. And there are a couple different time scales of that variation that we're going to be looking at on the next slide. The first of which being the 11-year solar cycle. That has to do with the structure of the sun's magnetic field and its evolution over time. So it takes 11 years for the sun to reverse its magnetic polarity. It switches north and south poles. And in that process, there are times where the sun looks like a normal magnetic dipole, and there are times where it looks really crazy and complicated and has all of these high non-dipole moments in its magnetic field. So whenever the magnetic field is complex, we are peaking, we see the most sunspots, we see the most UV emission, and then at the solar minimum, we will see less sunspots and less UV emission. And the change that we can expect to see in UV emission is about 10 times between solar minimum and solar maximum. So it's certainly significant if that's our main input into the thermosphere. The next thing we want to look at is solar events, such as a solar flare. So this plot in the middle is showing X-ray flux from our most recent X-class solar flare. And if you follow the red curve, you'll see that it jumps from 10 to the -6 to 10 to the -3 in intensity. So that's 3 orders of magnitude in a very short period of time. So as you can expect, this can have a large effect on the energy that's entering our atmosphere. And then the scale of this whole event is very short, lasting less than a whole day to go all the way up to that peak and then to come back down to the previous levels. So that's 2 wildly different scales we'll have to be able to take into account if we want to study the solar input that's affecting our thermosphere and ionosphere. And as a bonus on this plot here, not only do we have to worry about solar photons coming in, we also have to worry about magnetic activity that is communicated to the Earth through the solar wind. And this is a bit of a tangent, but this is on a similar time scale to solar flares. So if we really want to take full solar activity into account, we'll have to be interested in this magnetic activity as well. All right, so that's all the variability we can see from the sun. Next, we are going to talk about waves that are traveling up from the lower atmosphere. So before telling you what these plots are, I'd like to compare them. So we'll notice in each of them, there are these 4 peaks as we travel along in longitude. Certainly noticeable in this plot down to the bottom right. You have them circled with these ellipses. We have these 4 peaks in the globe here. We can see a similar 4-peak structure if we follow the equator in this plot. Now the plot on the left is data from NASA timed, and this is showing us generally ionospheric density. And this is from NASA trim, which is showing rainfall data. So it's not necessarily something that you would expect to be connected, but they are connected by a mechanism which is the solar tides. And we don't really have much time to go into the details of tides here. That would be a talk in and of itself. But some of this energy from the sun at other wavelengths besides the UV are getting input into the atmosphere at a much lower height. which is why we see the effects in the troposphere where rain and other weather events occur. And these disturbances and heat input, all of that travel upward into the thermosphere and are ultimately affecting what we see in the ionosphere. And I have one more plot to show that. One of the ways we model these tidal signatures is with a amplitude of a temperature wave, right? Temperature fluctuations varying in space and time. So in the blue on this plot, we have this tidal signature, right? And this is degrees, this is Kelvin. And then what we have in the black and red is once again ionospheric measurements. And this is actually measuring the separation of the two peaks of the equatorial anomaly, but it's related to the strength of the ionosphere. Some of this data is from NASA IMAGE, which is another upper atmosphere study satellite. So we can see that there's this connection here, but the mechanism by which this, temperature perturbations in the lower atmosphere is communicated to the structure in the ionosphere is something that hasn't really been fully studied, right? So that really leads us into ICON. What do we want to do with it? What do we want to see, and how are we going to see that? So just to sum up all of what we previously saw, right? We have this variation in solar activity and solar UV flux coming from the sun that's affecting our ionization and energy input to the upper atmosphere. And we also have these tidal waves in the lower atmosphere that are communicating this wave information up to us through temperature, through wind speed, and maybe through density. So how do we measure this mechanism by which those waves are changing the structure of the ionosphere? We need to see a vertical profile of these quantities that we think are going to fluctuate along with these tides. And measuring a vertical profile with a satellite seems kind of difficult, right? If we're up at the location of ICON at 600 kilometers and we want to see wind speed at 200 kilometers, that might seem something that's difficult. So how are we going to remotely sense that information? And the key to all of this is going to be Airglow. Now, later we'll get into how Airglow is going to help us, but first let's talk about what it is. Airglow is exactly what it sounds like. The air will glow at different wavelengths depending on the process that leads to the airglow and depending on what species is emitting these photons. So one such process that can lead to airglow is related to our ionization in the thermosphere of atomic oxygen. So we were talking before about how solar UV can come in and ionize these oxygen atoms, turning them into ions. So we have this depicted on this top line here. A high energy photon comes in and it knocks off an electron. We now have a photoelectron and an oxygen ion. But sometimes if we have a high enough energy photon, not only do we knock off an electron, but we bump one up into a higher energy state, we now have an excited ion. Now in lower atmospheres, when such a thing occurs, atoms and other particles have ways of transferring energy from one to the other by collisions. But up in the thermosphere, the mean free path is very long because the density is so low, and these particles can exist for a long time before they see any others. So we can start entering into the time scales that are necessary for them to radiatively de-excite, to release a photon and to re-enter into their ground state, right? And these photons are the ones that we see in the form of airglow, right? So depending on the species, we have green airglow, we have red, and then we have some in the UV as well. And we're going to be taking a look at all of these using ICON. So before we move on, just want to point out this cool picture taken from the space station that's on the right here. You can see the red airglow at a higher altitude than the green airglow on the horizon. So that's pretty cool. All right, so how is airglow going to help us? Well, first I'm going to tell you it's going to give us temperature profiles, it's going to give us wind profiles, and it's also going to give us profiles of ion abundance and atmospheric composition. So the best way to discuss how it's going to do these things is likely to look at each instrument. So giving us wind and temperature is the MIDI instrument. This is one of the I's in here is for interferometer. I think it's Michelson interferometer. I could be wrong. It's in my backup slides. Using interferometry, MIDI is able to measure the Doppler effect. At known wavelengths, we have emissions in the lower atmosphere, and MIDI is going to be able to measure the change in wavelength caused by the movement of these particles. And that's going to tell us the wind. And it's going to use a similar process to tell us temperature. There's an Airglow in the infrared, and then depending on the temperature, some of the peaks kind of shift around. So MIDI is going to give us temperature and visible wind. For ion abundance and for atmospheric composition, we need two instruments. So we have first the FUV, measuring far UV Airglow. It's going to give us, during the day, it's going to give us atomic oxygen and molecular nitrogen profiles as a function of altitude. And then our EUV instrument is going to give us O+ during the day. And then at night, FUV is going to give us O+. So between the two, we're going to know the ion abundance day and night. And then during the day, we're going to get the atmospheric O/N2 ratio, which is important for studying atmospheric composition, right? And then finally, not a remote sensing instrument, but an in situ one, we have the ion velocity meter, which is going to tell us ion density and velocity at the location of ICON, I'm sorry. So I don't want to get too much into this, but the reason that we include this in situ measurement in addition to these remote ones is that if we have these measurements along magnetic field lines, combining the MIDI measurement remotely with the ICON in situ measurement on the same magnetic field line, those measurements are able to be correlated, telling us more data about what's happening down here. So that's pretty interesting. But anyway, with all of these instruments combined, ICON is now able to tell us about some of these mechanisms that we think these lower atmospheric waves are propagating up into the thermosphere, right? Specifically the temperature, the wind, and the composition. And then we can see the ion abundance, which would be a consequence of these waves traveling upward. So that's pretty cool. And then here's the data product matrix for ICON. So you can see at the top, we have the instruments, and as you move down in level, the data retrieve becomes more complex, starting at level 1, which is pretty close to being the raw output of the instruments. And then I think the best place for us to look is at level 3. So we're getting winds, we're getting temperature, we're getting O/N2, which is composition, and then we're getting ion density as well. So that's pretty cool. That's ICON. These are in line with the science goals of the ICON mission to study sources of strong ionospheric variation and the mechanisms by which these lower atmosphere waves travel upward. So for the rest of the talk, we're not going to be talking about that. We're going to be talking about my research, which has been looking at some of this low-level data from the EUV instrument. So here we do a little transition from talking about ICON to talking about what I'm doing. And in order to do so, we need to take a little bit more of a detailed look into this before with the FEV and other instruments with the Airglow. Okay, so just a reminder, the purpose of the EUV instrument is to measure daytime O+ profiles in the thermosphere, right? And it's doing this by measuring airglow, as we alluded to earlier. The production of this airglow is from about 150 to 200 kilometers. Excuse me. So the light travels from this layer down here up into our detector at 600 kilometers in ICON, right? And we're using these two lines that are associated with O+, right? This is in angstroms 834 and 617. Now, why are we using two? Well, it might be helpful to take a look at each of them and what they're telling us. 617 does not scatter very efficiently. So it starts from where it's generated and it goes straight up to ion through this F2 layer without scattering or hardly seeing it at all. On the other hand, this 834 is generated down here and it does scatter. So it's all bouncing around so that when it arrives at our detector, it appears as if it originated up here when in fact it didn't originate down here. So it seems like, maybe we would just want to use 617, but 617 is very dim in comparison to 834. But hopefully by combining the two, right, we would then be able to get an idea of where this oxygen actually is, where this O+ rather actually is, oxygen ions. So the way the detector does this is it takes in through the baffle right here, the light comes in and it goes off a diffraction grating and onto an imager. So it's spread apart depending on what wavelength it is. And we'll see kind of an image of that on the next slide. But here I'd like to point out that the imager looks like a pug. So it gets the nickname of the pug. Had to throw that in there. So this is the EUV instrument. For the rest of the talk, we're going to be kind of looking at this thing. All right, so here is kind of an idea of what the actual detector is picking up in the EUV. So each pixel in this image would represent a pixel on the detector, and this is summed up for a whole day. So the color is a log scale of brightness or counts, and we can see that the tubes that we want to look at are here at 61.6 nanometers and 83.4 nanometers. We're going to switch from calling this 617 to 616 now because of some of the ICON documentation. And we're also going to move from talking about angstroms to nanometers, but please interrupt me if you ever get any of them mixed up. So these are the two lines we want to look at, but looking at this image, you'll first maybe notice that we have other things coming in, right? Other lines of Airglow. And in particular, there's this very bright one right here, and that's helium 584 that's coming in right there. And this is a bright line and it extends all the way up. So this is the vertical dimension right here. The ICON EUV imager retains one physical dimension, but it trades its horizontal imaging dimension for wavelength. So we have this helium emission that's very bright and close to this 616. So in the design of this instrument, it was designed with such spectral resolution that it could tell these two apart, right? So you have to be able to resolve something that's about 3 nanometers from each other. And as a result of that, we get out of this instrument all this other data that it wasn't specifically designed to measure, right? We get all of these other bins that are going to pop up in our level 1 data. So the data that we're going to be looking at is at each of these wavelengths, right? It's going to be centering a bin, and we're going to integrate horizontally, essentially counting a little bit of a band around each of these wavelengths, and then that will give us the brightness at a given altitude. So this is what that data looks like, not for a single exposure, but for several exposures added up for a month. You can imagine that each of these dots on each of one of these plots is an integration across some wavelengths for a given altitude bin on the detector, right? So this is not all of them. There are 12 in total if you feel like counting on the bottom. Just showing you 6 of them. You can see that these 3 are our main science lines that were taken into account when designing the detector. We have our 616 and our 834. And first of all, compare the brightness of the two. Like I said, 834 is much brighter at around 400 to 600 Rayleighs, whereas 616 in the same altitude range is 20 to 60, so we're easily 10 times brighter in 834. But some of these bins that were getting reported are very dim, such as the 741, peaking out at maybe 10, maybe 15 Rayleighs. So we're seeing some bright lines and some that are very dim. In the brighter lines, we get this nice kind of profile. You can see how it is evolving over altitude, whereas some of the dimmer ones, when we just have it scattered like this, it looks like a blob. Now, when looking at this data, the first thing that we notice is that there is kind of a secondary population going on in some of them. This data was termed the heel, because if you look at 834, you've got like a nice little platform shoe looking heel. So we have at the same altitude a much lower flux being reported. So my first kind of goal was to discover what was creating this. Why do we have this second population going on? In order to do that, the first thing I looked at was, we can visibly see it on the scatter plot in 834 and 584 and this 878 a little bit as well. But for example, take a look at this 537 and you can't see anything, right? It just seems like one kind of solid body. So we're going to look at all of the other wavelengths and see if at the same times of these observations, the brightness is lower. So that's what all of these plots are. In the purple, you can see the total average over all times, and then in gold, you can see the average during heel time observations. That is defining heel time by when we're into 834 heel. And you can see that this is in fact something that's affecting us at all wavelengths, even to a statistically separable degree for some of them. So this is definitely something that was worth our concern about. So next we looked at where these observations were coming from. So for December to April, I plotted the ICON location during all of these heel observations, and you can see that they're all kind of in the same spot on the globe. Now, if you work with any satellites, you may see where this is going, because there's something special about this region, and that is the South Atlantic Anomaly. So the South Atlantic Anomaly is an area on Earth where the magnetic field is the weakest, and as a result, more high energy radiation penetrates to lower altitudes in low Earth orbit. So you can see in this plot here, this is high energy proton flux at, let's see, it says at 500 kilometers, right? So this is below where ICON would be flying. And there's this one region where we have this very high proton flux. So this can be damaging to equipment on satellites. So when ICON passes through this region, it turns down the voltage on the UV detector, on the EUV detector. And that's why we have gaps in the data. If you ever look at plots that have the ICON orbits on them, you will see some gaps around South America because of this anomaly. So if we flag all of the points that are when we come out of the South Atlantic anomaly, we can see that's what's generating our heel. This is because whenever the detector turns the voltage back up, it doesn't quite get back up all the way in time for the first measurement. So we're getting kind of like this half turned on. If you ever turned on one of those CRT TVs, after maybe a second, it's full brightness, but you can kind of see something. That's similar to what we're getting here. All right, so that was our first little thing, but now operational concerns out of the way, we were able to do some science by comparing all of the smaller secondary bins to the ones that we already know what we have. That would be our 616 and our 834 that we're trying to measure to find the location of O+, and this 584 that tells us about the location of helium, right? So we compare all of the other wavelengths to these. So for example, we'll run through the process for 555, right? So here is the average altitude profile for that wavelength. We have it separated by high and low solar zenith angle, essentially the amount of sunlight that's coming in at the tangent location. And what we did was we took the ratio of brightness between two wavelengths at measurement time, right? Because we look at this, we already don't know, it looks like, we know it doesn't look like the helium line because it's not just a vertical line, but it looks like, you know, it could maybe be oxygen related. So by comparing it to these known oxygen emissions, we can maybe, you know, see if it's something that is a rock steady link. And looking at 834, we can see that it's not, right? This is something that's kind of zigzagging on the way up. Whereas if we compare it to 616, we do have this kind of vertical line up to a certain point where it then just takes off. And as to say that this dim 55.5 nanometer line is becoming much brighter than this 616, which we intend to measure at high altitudes. And this is in fact something that happens for a lot of our wavelengths, giving us, you know, two conclusions that pop out. That either this is something that's physical, and that maybe similar to 834, these are scattering at very high altitudes, which is, in my opinion, not super likely, right? Because it doesn't look like the profile of 834. Another possibility then would be that there's some error with the background correction and calibration of this 616 line, and that it's artificially dim at these high altitudes. So that's kind of something put on the back burner for now. But at least down here where we expect this light to be generated, we have kind of this straight line pattern, so that we can, you know, maybe kind of conclude that we have correlation here, that it's likely that these wavelengths are related to O+, right? And by going through that process for every wavelength, then we can identify things that we expect to be dominated by O+ emissions, right? And things that we think maybe could possibly be dominated by O+ emissions, right? Which is exciting because some of these were previously known and some of them were not, right? So 741, for example, there's this dim emission you can see. And in our main literary resource, there wasn't any indication that we should expect to find an O+ line there. And yet we've determined, you know, with at least some certainty that there is an O+ type feature that's lying around there. So that's really cool, kind of our first result. But you'll notice that there's this one bin here that has not found a friend, right? Not even a questionable, you know, maybe this is oxygen friend, like a truly, we have no idea what's going on. So we took a little bit of a deeper look into that one. This is 87.8 nanometers. And as you can see, it peaks at a fairly low altitude. And it's a sharp peak, not like this kind of flat 834. And when we look at the ratios versus altitude, you can see it's kind of going crazy for both 616 and 834. So there is a known nitrogen emission at 87.5. So we thought, what if we're picking up that nitrogen? That would be really cool. It's something that wasn't being planned. And furthermore, if you'll recall, the FUV detector is being used to measure N2. So if we can measure nitrogen with the EUV detector, that would be very helpful, right? We can corroborate against the measurements that are already being taken in the FUV, since we expect this N and N2 to be related. So to kind of test that hypothesis, you know, maybe we can find some information about nitrogen from this line. We took the ratio of 616 to 878 and looked at that over time, right? Because this quantity that's important for N2 is the O to N2 ratio. So by comparing 616 to 878, we've created kind of this pseudo like O+ to N ratio, and maybe we'd expect that to follow a similar trend over time. Here, I'm mindful of the time, we should be finished fairly soon. We have these two plots that show the latitude structure of the actual O to N2, what we want to compare to. This is measured by ICON FUV, and you'll see that In January, this is Northern Hemisphere winter, we have these low ratios down at low latitude, and as you move north, the ratio increases. But then the trend is flipped in the Northern Hemisphere summer, where we have a high ratio at low latitude, and as we move northward, the ratio decreases. So what we did is we looked at this for our 617 to 878 EUV ratio, and it's hard to tell on this color scale, and the effect is slight, more subtle than for the FUV, but you can see in January, we're moving from this low ratio with the green and yellow up to the red and orange at higher latitude. And then in May, the trend is reversed, right? We have red and orange down here and yellow up in the high latitude, right? So this is an encouraging result. But since we're doing a climatological almost comparison over a long period of time, we figured it would also be good to compare to MSIS, which is a climatological model of the atmosphere. So what we have in blue here is the MSIS O to N2 ratio at a given local time and latitude range for certain sections of the year. And in black, we have our quantity of interest, this EUV ratio. And you can see that the two are following each other fairly closely. So once again, this is very encouraging, telling us that, maybe we are seeing something that is telling us about in or into, which would be exciting. So next, we wanted to look and see what's happening on a measurement to measurement basis. So for a given measurement of O to N2 by the FUV instrument, how is our kind of pseudo O to N2 measurement stacking up, and how is it changing over time? And we couldn't compare it to the O to N2 reported by ICON itself because of some issues with geometry, but we were able to go into the FUV level 1 data and do something that we think is similar. So on the x-axis, we have scattered the EUV ratio that we've kind of invented, and then we have the FUV ratio that is inverted through some process to get O to N2. The ratio itself might not be a part of it, but the two components are. And we can see for January and June, we're getting some really good correlation here between our made up O to N2 ratio and something that's more like the real thing, which is really encouraging until we looked in the spring and it gets significantly more dicey. February seems all right, but March is a blob, and by May, we're getting kind of two populations again. So that's kind of where we are right now, trying to find out, is there something going on with the instruments here? Is this something that, maybe we're taking a bit of a naive approach and maybe need to, take a more complex one, or, maybe it's a dead end and it won't lead anywhere. But that's where we are. So to conclude, from my research, we have identified some of these features that are reported by ICON that certainly seem to have some O+ features within them, possibly leading the way for us to identify some more O+ lines in the upper atmosphere. And then finally, we have this 87.8 that we think is at least related to nitrogen. And if we could use it to measure O to N2, that would be really exciting. But if not, it's at least fun to take a look at. So yeah, that's it.
All right, well, thank you very much, Richard. Thank you very much. Just we'll take your part at the bottom of there. This is time for any comments or questions from anybody of our participants, and certainly join me in thanking Richard here for giving a presentation here today. Maybe I'll start off with one question or something. Maybe it's not something you might know of, but that heel data was very interesting and very it's a very cool find, I guess, is something that relates to radar operations. Is that something that they had planned for or tested, or is that something maybe that was kind of unexpected once the satellite started taking data?
It's funny you should ask. So the heel the HEAL files, the way that ICON reports the data is a file for every single exposure. And the fix was eventually to yank out the files that had these kind of bad HEAL exposures. Now, at the time that I discovered the HEAL, there had been a fix implemented, but I don't think everyone was aware of it because of kind of the structuring of the versioning and revisions of the data. So it's something that the team was aware of, but it's something that was brought to more prominent light, I suppose. I don't know if that answers the question.
Yeah, I think a little bit. Yeah, I'd say it's something. I guess they might not have. Maybe I guess they were planning on turning it on and off, but not having it have as much of a warm up time or something like you could say with the related to the CRT.
That's exactly kind of what our thought process was, that maybe the detector was taking longer to turn on than they thought. And that may have been a factor in it, but that has been corrected and I think was anticipated.
Okay. Yeah, it's a neat find. Any other comments or questions for Richard? I haven't seen anything come up on the chat to me or anything. I know the mute button can be a little tricky to find.
If there are no questions, I first of all just want to thank everyone for coming. It was a pleasure to be here, and yeah, really cool.
Yeah, very good.
Great presentation.
Thank you.
Yeah, with that, if there's nothing else, feel free to try to jump in and interrupt me here. But otherwise, thank you very much, Richard. And again, for everybody on the line here and maybe watching later, we'll have our first joint seminar with the Center for Geospace or Center for Geospace Storms next week, next Thursday, and then Ginny Smith will be presenting for us in 2 weeks. So otherwise, thank you very much for joining, and I'll be hanging out for a little while. So thanks.